Okay, should be a fairly brief lecture today. I thank you all for showing up. So today's about the thalamus, and you know, a lot of this can be summarized in a single table, which we'll see in a little bit. So that's cool. Besides that, there's just a couple of things that might be tricky to you, and those are going to be those non-specific nuclei, the intralaminar and the reticular nuclei. Everything else is extremely straightforward, and it's really all right here. There's going to be some lower input. Let's say our ventrolateral nucleus, for example. It has input from the cerebellum, so you know it's going to be involved in motor function. There's always some lower input, and then there's reciprocal connections with the cortex. And so in this case, the ventrolateral nucleus, which gets input from the cerebellum and basal ganglia, outputs to the supplementary motor area and the primary motor cortex. That tells you it's critically involved in motor function. It's an important motor relay nucleus. The excitability of our primary motor cortex depends on that excitatory input from the ventrolateral thalamus. Pick another nucleus, it's going to hit a different part of the cortex. That's it. So I've also color-coded this a bit to make it a little easier. So I colored these blue for sensory, motor is green. You can see it's a little anterior to sensory here. So what we're doing is looking down on top of the thalamus. So imagine that you've sliced my head open there, removed the cortex. There's another thalamus over here. We're looking top down, anterior, posterior. Green is in front of the blue, motor is in front of the sensory, just like it is in the cortex. Your primary motor cortex is going to be right in front of your primary sensory cortex. Motor tends to be more anterior to sensory. This is also true in the spinal cord as well. Your posterior columns are sensory and your corticospinal tract is anterior to that. Then there's these red nuclei that are going to have connections with the limbic system. Sometimes they're going to be involved with memory and emotion. So when we cover the limbic system in the next lecture, these nuclei are going to be important relays for those areas of the brain, whether it's hippocampus, mammillary bodies, cingulate cortex, prefrontal cortex. So we're going to walk through these nuclei one at a time just to see their targets. We'll lump them together to be a little more efficient. And then we'll touch on the intralaminar nuclei, which I just put here. They're scattered all throughout though, and there's a bunch of different intralaminar nuclei that hit general areas of the cortex. We're going to lump them all together though. We're going to say that these colored ones are specific, even though they're not totally, and we're going to say that these are diffuse. The reticular nucleus is very different from these others. So in the main thalamus here, these are all going to be glutamatergic projection neurons. So excitatory output. In this case, inhibitory. This is going to be our filter. So we're going to have diffuse lateral inhibition so that only the most excited neurons are going to communicate with the cortex. So this is to give us a little more specificity. Just like we've seen everywhere else, there's always some inhibitory neurons that are providing sort of diffuse inhibition. Essentially raising the bar for excitation. That's the purpose of the reticular nucleus. So we'll go through this first part here. We got our relay nuclei that are just going to hand excitation from lower tracts on up to the cortex, like your LGN, for example, in the last lecture. Your optic tracts are going to target the lateral geniculate nucleus. The lateral geniculate nucleus then communicates with the primary visual cortex. It's just a simple relay, sort of. Then there's associational nuclei that are going to lump together different bits of information, maybe visual, somatosensory, and auditory, so we can start to have a clearer picture of what's going on right now. So we're not looking at just individual pieces of information. We can integrate multiple senses, which is what you're doing right now. You hear, you see, you feel, maybe you smell, and if you do, I hope it's pleasant. But you're doing all that at the same time. And in order to experience all that together, you have to have integration. Like if you're going to compare red and green, those neurons have to meet up somewhere. It's going to be in the LGN. So this relay Really what we're talking about is the communication between the thalamus and the cortex. That thalamocortical signaling is what's going to determine kind of our level of consciousness. If your cortex isn't highly active, you are not conscious. And the activity of the cortex is going to be critically regulated by the thalamus. This is an important source of excitatory input. And really there's two types of thalamic projections. There's the ones that we're going to talk about today. Those would be the core projection neurons. They're going to hit layer 4 of the cortex. More on this in lecture 23. They're going to communicate with neurons in layer 4 to excite specific areas of the cortex depending on where they target. In the more anterior regions, they're going to project more anteriorly. Posterior regions project more posteriorly. So that the area makes sense. Those thalamic neurons up here aren't going to project back through. There's an orderly arrangement. Those on top tend to project upward. Those on the bottom tend to project downward. And they project via these thalamic peduncles. They're just collections of axons. Their names make sense. The anterior goes anterior, posterior goes posterior. So we just have these bundles of communication. These are two-way streets, back and forth, from thalamus to cortex, cortex to thalamus. Anytime we're linking thalamus and cortex, keep in mind those are reciprocal. There's a back and forth. The thalamus is going to be an important filter to determine what do we pay attention to. There's another set of neurons, kind of more diffusely scattered throughout what we call the matrix neurons, and they don't target layer 4 in specific areas, they target layer 1, so the most superficial area of the cortex, and these projections are far more diffuse. So when we look at the map today, what we're looking at is core. The matrix neurons are going to defy this. They're not going to hit just one specific area of the cortex, it's going to be more diffuse. This is just going to allow for integration. We're going to forget that that exists for the purposes of today's lecture. Of course, when you're out there in the clinic, that's all you're going to think about. So those core neurons, some of them are going to hit motor areas. The two nuclei for motor relays are going to be your ventral anterior and lateral, colored green up there. So when we're talking about the output from the basal ganglia, here's the target. So that inhibitory input from your SNR and GPI, that's going to hit your motor nuclei. And that's how we're going to either allow or inhibit the execution of motor programs. So if we provide inhibitory input here, then we prevent excitatory feedback to motor areas of the cortex. Those more involved with planning, that's going to be your ventral anterior target, so prefrontal cortex. This is where we have conscious awareness constructed. And then your premotor area is important for motor planning. More on that in lecture 23. Supplementary motor area is more involved with multi-step tasks. Primary motor cortex, these are components of the corticospinal tract. All these are to some degree, even your somatosensory cortex. But the primary motor cortex, think of this as your principal upper motor neuron. If we don't excite them, we don't excite lower motor neurons. So that inhibitory feedback from the basal ganglia determines whether or not we have excitation then of our motor areas and actually do something. When the direct pathway is active, there's selective inhibition of the output and selective disinhibition of the thalamus, leading to selective excitation of upper motor neurons. There's also input from the cerebellum as well. This is going to hit the ventral lateral nucleus, and this is going to help refine which upper motor neurons do we pick in order to carry out whatever it is we want to do. Whether it's just take a step, touch your nose, juggle, doesn't matter. The cerebellum is going to feed back here, and from the ventral lateral nucleus then affect motor cortex. That's how we're going to refine movement here. So there's your motor nuclei. The sensory nuclei, a little bit behind that, your dorsomedial is a mix. It's going to deal with olfaction. So that's the sensory component. But then there's also this cognitive component because of its connections with the limbic system. It can affect memory circuits, emotional circuits. The other sensory aspect here is going to be the pain pathways to create the affective component of pain. Pain sucks. And the reason that pain sucks is because we're targeting the dorsomedial nucleus, which then recruits limbic structures to produce that emotional response to pain, so we don't like it. Pain's instructive too. We learn from pain. Again, we're involving the limbic system. Memory. Fire's hot. You don't need to repeat that. Once you burn yourself, you pretty well learn. These other nuclei are just sensory relays. Aside from our posterior lateral and pulvinar. These are a bit different. So these are associational nuclei because they actually get input from primary sensory cortices for vision, your primary auditory cortex, and your primary somatosensory cortex. So those parts of the cortex that are figuring out the granular bits of information related to vision, hearing, and touch, those are going to combine and converge here, gesundheit, so that we can integrate that information and we can take multiple senses into account. The pulvinar and posterior lateral nuclei are also connected with associational cortices. So here's how your primary cortices can communicate with associational cortices. There are some fibers that are going to connect them, but they can also integrate at the level of the thalamus. So those parts of the cortex that only deal with somatosensation, only deal with vision, and only deal with auditory input can then hit other areas of the cortex so that multiple pieces of information can be integrated. If I want to reach out and grab my glass, I need to know where my limb is. I need to know where the glass is. So I need to take into account visual and somatosensory information. If you're going to do that, they have to converge. That convergence is going to happen here in the thalamus and then in those association cortices. So here we're putting together multiple pieces. The rest are just going to be pretty simple relays. Lateral geniculate, that's from last lecture. So those optic tracts come in. We create a retinotopic map. So those retinal ganglion cells that are near one another in the retina are going to target LGN neurons that are near one another, so we preserve that spatial relationship. The medial geniculate nucleus, that's back from cranial nerve 8's lecture. So auditory input from the cochlear nerve. That's going to arrive in the brainstem. Cochlear nuclei then project to the medial geniculate. From the medial geniculate, we go to the primary auditory cortex. And then we have the ventral posterior nuclei, somatosensory. We have a map of the retina and the LGN. We have a map of different frequencies in the MGN. And of course, we have a map of our body in the ventral posterior nuclei. There's a medial nucleus and there's a lateral nucleus. So here it is projected up here. So the more anterior portions, these deal more with proprioception. The fine touch is a little more posterior to that, and those painful pathways that come in are going to be a little more posterior there. So we actually have multiple body maps. And each of these body maps is going to have our head in the more medial portions, and the lateral portion is going to have the rest of our body. So we'll have a pain map, we'll have a fine touch map, and we'll have a proprioception map as well. Multiple maps in our ventral posterior nucleus. From here, we're heading up to our somatosensory cortices. And this is where we're going to start to create the perception of touch. Whenever you actually feel something, I feel this in my hand, but that's not really true. My hand doesn't really feel it. This is what feels it. You can lose a limb and still perceive pain or the sense of movement in that limb, even though it doesn't exist. The fact that I feel this right here is really an illusion that I'm creating up here, and the way that it gets there is through the ventral posterior nucleus of the thalamus. If that weren't true, how would we have phantom limb pain? How would we have phantom sensations? Even people born without limbs can perceive movement in those limbs that never existed. And that's because we have these body maps ingrained. So we're not quite there. We're not quite to where the magic happens, but we're talking to it back and forth. We're gonna determine what kind of magic happens. That's going to be in the second part of this. So the thalamus is a really important relay for motor, sensory, and cognitive functions as well. So your dorsal medial is still here because of those connections with the limbic system. So this is going to be an important part of our memory circuits that we create. So the way that our hippocampus can influence the cortex? Well, there's direct connections with the cortex from the hippocampus, but we also have a thalamic relay. And we'll talk about that in the next lecture. We'll go from the hippocampus to the mammillary bodies to the anterior nucleus, and then on up to the cingulate. And then we're in the cortex. So these red nuclei here, your anterior, your lateral dorsal, and your dorsomedial nuclei, are going to be our cognitive nuclei. So they're going to help us create our emotion, and they're going to help connect different memory circuits, whether they are in the limbic system here or in your prefrontal cortex. This is where we create consciousness. That's the thought anyway. It's still really mysterious. But we think it has to do with the prefrontal cortex. So those memories that we store, at least for a short term, anywhere from minutes to years in the hippocampus, can be brought into our conscious perception, in part via thalamic relays. There's not really a whole lot to go over here. I know there's a bunch of different nuclei and whatnot, but it's pretty straightforward. If you're carrying visual information in the optic tract, first you stop off here, then you go to the cortex. That's about it. And so as long as you can organize this into a table like this, you'll be fine. You don't need to remember all these things. You need to know that the thalamus is a relay, and that's probably about it. When you have damage to the thalamus, you can have widespread effects in the cortex, because the thalamus is much smaller than the cortex. But everything that makes it to the cortex goes through here. So a small lesion in the thalamus will give you major problems in the cortex, because we kind of put all our eggs in one basket, if you will. We collect these sensory pathways just right here. Now, the somatosensory cortex is much bigger than your ventral posterior nucleus. If you damage that, no more somatosensation. Your relay is gone. And if you don't make it to the cortex, it doesn't exist. It's not real. And hell, even if you make it to the cortex, it might not be real. Again, that's that phantom pain. So we can spend time going through this, or we can just click through them. You know, so your motor planning has these two. And the reason it has to do with motor function is because of where it's hidden in the cortex and the types of inputs. Your filter and your muscle memory is going to feed into these nuclei, and they're going to inform what are we doing in our motor cortices. Your sensory cortices, down here, all the different senses and multiple senses are going to hit different thalamic nuclei, and those are going to hit different parts of the cortex. The reason that the ventral posterior nucleus is involved with somatosensation is because it has somatosensory afferents that feed into it, those secondary afferents in our posterior column, medial meniscus, spinal thalamic tract, and trigeminal thalamic tract hit there. From there, they go to the primary somatosensory cortex. Just that simple. It can't be involved in anything else. It has to be somatosensation. If it had input from, let's say, the inner ear, of course, via those brainstem nuclei, then it would deal with something different, like auditory input. But it doesn't. That's what our medial geniculate does. These bottom three are going to be more involved with cognitive functions, like memory and emotion, just because of their targets. We're going to be hitting structures in the limbic system. Hippocampus is absolutely critical for memory function. So are the mammillary bodies. Because the limbic system is widely connected with itself, we can also affect emotion as well. Your memory and emotion circuits are critically tied together. So I don't want to dwell on this, because you can put it into a table. Hell, I've already done it for you. And you can use that table on the exams. I just want you to appreciate that there are specific relays. What I think is probably a little more difficult to understand is this next part. So the non-specific nuclei, not the specific relays that we just went over. These are going to have a little more diffuse patterns of connection. For the intralaminar nuclei, diffuse excitatory projections to the cortex. For the reticular nucleus, diffuse inhibitory projections within the thalamus. So we'll go over the intralaminar nuclei first, and then we'll spend a little bit of time on the reticular nucleus. So it's fairly important. The the intralaminar nuclei are just kind of spread around in between those different specific relays. Like here's your mediodorsal nucleus, here's your lateral posterior, lateral dorsal, ventral posterior nucleus here. In between that, we have these kind of poorly defined intralaminar nuclei. So they're between the different discrete sensory relay and motor relay nuclei that we just went over. So scattered throughout there, we have these neurons that have wide diffuse projections within the cortex. So they're going to cause just sort of general excitation, and that's going to synchronize cortical activity. They're going to be a little more active whenever we're awake. So they're going to have widespread excitation of the cortex, which is going to help actually make us awake. So that ascending arousal system is going to stimulate these neurons. And their purpose here is to essentially allow for us to function, to allow the cortex to more effectively communicate with itself. So that if you're trying to carry out a motor program, for example, you're not going to have two areas that need to communicate met with one being excited and the other inhibited. You're going to synchronize their excitation so they can effectively communicate with one another. And it's kind of, I think, difficult to visualize by looking at these sine waves. It kind of makes sense, I suppose. But let's look at some actual data here so we can see what this is doing for us. I think this might be helpful. So I put this in the last minute. So here's what they've done. They've expressed this light-sensitive ion channel called channel rhodopsin. That's CHRT. They put this into some inhibitory neurons that will come in and inhibit intralaminar nuclei. And so we'll see how that works in just a second. So we're making our inhibitory neurons excited by blue light. And all you got to do is jam a fiber optic cable into the brain and shine some blue light in there. Not too difficult to do. And when you do that, you're going to open up ion channels and drive depolarization. So we can directly control the output of these inhibitory neurons with blue light. And in fact, when you shine that blue light, the firing of action potentials pauses for these intralaminar neurons. So here they're recording from intralaminar neurons. This is control, no channel rhodopsin. So when you shine blue light in the brain, not much happens, unless you put in this light-sensitive ion channel. So the bottom is control, no effect of blue light. Up top, turn on the blue light, stimulate inhibitory neurons. Your intralaminar neurons aren't firing. So what happens then to the activity of the organism? That's a little more interesting, I think, here. This is just to say when you put on blue light, your intralaminar nuclei are inhibited. So their diffuse projections to the cortex aren't being stimulated. They're not grossly exciting the cortex and synchronizing activity and allowing the execution of activity, and that's precisely what we see here. So here's control. This is the amount of movement in the animal, so they're just freely moving. They have fiber optic cable jammed into their head, but it's attached to an apparatus that allows them to run around their cage. And they just look at the amount of movement. And mice run around. 100% is just normal movement. They're just running around the cage. This solid line here is when they put in channel rhodopsin. So now when you shine the blue light, you inhibit your intralaminar nuclei. What do we see here? Any effect? I hope so. Yeah, exactly. Locomotion goes down. It becomes difficult for these mice to initiate action as a result. So the purpose of our intralaminar nuclei, what we think right now, is just to allow the cortex essentially to do its job. The amount of excitation that we give from our intralaminar nuclei is going to help the cortex be excited enough that we can actually perform a function. And when you lose this, you see activity drop down. It's more difficult to initiate action because there's a couple of targets. The cortex, the striatum. So we're going to be affecting the cortex, also the basal ganglia. The cortex is probably going to stimulate arousal, and of course the basal ganglia is going to determine should I do this or not. Action selection there. So that's the purpose of our intralaminar nuclei. Widespread excitation so that we can do something. When they're not active, like when we're asleep, for example, do we do stuff? Yeah, not as much stuff. We dream, we breathe, But for the most part, we just kind of lay there. The reason that we don't do as much stuff is because we're not widely exciting the cortex. It's difficult to recruit those neurons. Plus we have the sleep atonia. That's going to play a role too. But even in slow wave sleep, you're not doing much. And that's because your cortex isn't excited as much. And that's the purpose of our intralaminar nuclei. Excite the cortex. The reticular nucleus is there to determine which parts of the cortex should we excite. This is your filter. So wrapping around the rest of the thalamus is the reticular nucleus. Everything that's going into and out of the cortex is going to pass through the reticular nucleus. So here's the thalamus, here's the reticular nucleus, internal capsule, striatum. So the cortex is up here, thalamus is here. Those back and forth connections all pass through the reticular nucleus, and they're going to make a little collateral to excite reticular neurons. These are unique in that they're GABAergic. So this is what makes them different from the other neurons that we've discussed thus far. Everything else has been excitatory. These are GABAergic. So all of that communication between the thalamus and cortex is going to stop off in the reticular nucleus as well. This is going to provide a little feedback inhibition. There's also input from the ascending arousal system to regulate this inhibition, most likely through alpha-2 adrenergic receptors. So when we're awake, we're going to inhibit parts of the reticular nucleus. This is going to increase the excitability of the thalamus. When we're asleep, we're not inhibiting as much. We can inhibit the thalamus. The output is going to go back to all of those nuclei that we went over in the first part. And it's going to be fairly widespread. Here's two different reticular neurons. One's colored green, one's colored red. You can see, even though they're right next to each other in the reticular nucleus, you can't even tell their cell bodies apart. That's how close they are. We'll see why they're that close in a bit. They're going to target very different areas of the thalamus. So they're going to provide inhibition here in your anterior dorsal, here in your lateral dorsal nucleus. So they widely inhibit the thalamus. This is, again, raising the bar needed to excite these thalamic neurons. So weak excitation isn't going to cut it. This is going to cut down on noise. Because neurons aren't just inactive, waiting silently. We want to filter that noise out, though. That little just chance excitation of neurons, we don't want that to make it to the cortex and produce hallucinations or things like that. So we're going to filter it out with our reticular neurons. We're going to provide that widespread inhibition. And the degree of inhibition that they provide is going to change depending on the task that we're carrying out. So we can have selective attention. Certain things can get through, like if you're concerned more with feeling around in the dark to find an object, like your laser pointer. Maybe you wake up in the middle of the night and want to give a presentation. Who knows? You don't really care much about visual input at that point. You can filter that crap out and focus more on somatosensory input. Let me feel around. Vision's not going to help you as much. You can only have so much activity in the cortex anyway. So we're going to filter out the stuff that doesn't matter and let what we do want move on through. We'll get to that in just a bit. So these reticular neurons are coupled to one another with gap junctions. I forget which lecture this was in. 5? I don't know. They're the same thing that they were back in that lecture. Here we form little holes where we share our cytoplasm. So the cytoplasm is continuous between neighboring reticular neurons. Here's why we think this. Here's two neurons. This is their cell body. 1, 2. These things coming off, those are the pipettes that they're recording with. We're recording for cell 1, cell 2. And we're stimulating or inhibiting cell 1, stimulating or inhibiting cell 2, and looking at the activity in the other cell. So when we, let's say, depolarize cell 1, it fires a bunch of action potentials. No surprise there. What happens over here in cell 2? Even though we're not stimulating it, that charge transfers passively. And you can see it gets excited. So this allows your reticular neurons to act as a single unit. Because when one is depolarized, that depolarization spreads immediately and passively through gap junctions. When one's inhibited, so is its neighbor. If they do the same thing where they then stimulate cell 2 and just record in cell 1, you see it's a two-way transfer of charge. Of course it is. So these reticular neurons are going to have electrical synapses with one another rather than chemical synapses. And that allows them all to kind of function as a unit. Now we're going to have different populations of reticular neurons. It's not that the entire reticular nucleus is coupled together. But neurons that are a part of a similar function are going to be coupled together, so they all act as one. So the purpose of this, again, filter out any weak input, so only robust input makes it to the cortex. Because if we affect cortical activity, we affect our perceptions. So we don't want any noise affecting perceptions. The other function we can see up here, selective attention. So for this task, what they did was train mice to either listen to a noise, auditory input, or a light, visual input. That's going to tell them which switch to press to get their reward. There's two types of noise that they gave, and that's what told them either listen to noise or listen to light. And they presented the noise from one of two speakers, either on the left, hit this one, right, hit this one. Two types of noise. So there were different auditory cues, and the mouse learned when I hear what we're calling the brown noise, pay attention to the light. When I hear the blue noise, pay attention to the sound. So when they present sound on one side, light on the other, the mouse learns to pay attention either to vision or hearing. So if this were, let's say, brown noise presented to the left and a light presented to the right, the mouse learns I go press the right. If it were blue noise and has to attend to the auditory input, it's going to hit the left. It's going to ignore the visual input. So this is how they've taught the mouse selective attention. There's two conflicting pieces of information. Which one do I pay attention to? Well, that depends on the activity of the reticular neurons. Which input's going to make it to the cortex? Whenever we present brown noise, pay attention to visual input in this case. And they record the activity of the reticular neurons that are going to target your LGN, so the visual reticular neurons. Their firing went down. That's what we're looking at here. So these are just raster plots. Every little line is showing you action potentials in these visual reticular neurons. And here it is plotted over time. So this and this, same thing, a little easier to see here. When they present the cue to say, pay attention to visual input, we get a decrease in firing in our reticular neurons. In other words, we disinhibit the LGN. So it's more excitable, it's going to stimulate the cortex more, and your perception is largely colored by visual input rather than auditory input. On the other hand, if you need to neglect that visual input, instead listen. When we play the blue noise, saying pay attention to this auditory input, select the left, not the right, pay attention to auditory input. The way that we forget about that visual input and don't attend to it is with an increase in firing of those visual reticular neurons. So when you want to not pay attention to vision, as is the case here, those reticular neurons become more active and inhibit your LGN. So visual input has reduced impact on cortical activity, so you don't pay attention to it. Anything you're paying attention to, the only reason that you're attending to it is because it's influencing cortical activity. You're listening to the words that I say, it's influencing your cortical activity. You could choose not to pay attention. In that case, the reticular neurons targeting your medial geniculate nucleus would be more active and they'd inhibit it. And you'd filter this crap out. You'd maybe attend to the visual information right in front of you. That's how it's going to act as a filter. Different reticular neurons can be more active or less active to inhibit or disinhibit the target nuclei. What makes it through the thalamus? It depends. Which part isn't being inhibited by the reticular nucleus? That's what's going to give us selective attention. Pretty nifty stuff. This is also working when we're asleep too. It's still filtering what makes it through the thalamus. If you've ever heard of sleep spindles, These are these little bursts of activity you see kind of early on in the stage 2 of slow wave sleep there. Those bursts are caused by bursts of reticular thalamic activity. So it's little bursts of inhibition of the thalamus. That's what we're dealing with there. When you're asleep, you are largely inattentive to sensory input. You're sleeping, all the noise that's going on around you, any auditory input, not going to affect you. It has to be very loud to make it through. And that's because we're inhibiting those sensory relay nuclei. The reason that it doesn't influence our cortical activity is because it just doesn't make it. The reticular nucleus heads it off at the pass. What we're looking at here, these are sleep spindles recorded via EEG. So these little large amplitude bursts here, that's a sleep spindle, and that tends to coincide with bursting of reticular neurons that are going to target sensory nuclei, like those visual reticular neurons. Not so much for neurons that are going to target more limbic nuclei, like your mediodorsal, your anterior nucleus. What we instead see there is a decrease in activity in these reticular neurons. So we see an increase in sensory reticular neuron activity. That filters out sensory input. We don't care about that. We're sleeping. Instead, what's going to influence our cortical activity is activity in the limbic system. So your memories. This is part of the reason why your memories are going to kind of creep into your dreams a bit. Things that are going on in your life can influence your dreams, because activity in the limbic system essentially gets the green light. We decrease activity in our limbic reticular neurons. So now we're not inhibiting traffic flow in those limbic relays. So now the cortex is going to be driven not so much by sensory input. That's filtered out. It's going to be more involved with memory. Part of the reason why we think that sleep spindles are so important for memory consolidation is because of this. If you're going to consolidate a memory, if you're going to transfer it from the hippocampus to the cortex, your hippocampus has to be able to influence cortical activity. That means we're going to need to disinhibit those relay nuclei, and that's exactly what goes on in a sleep spindle. We inhibit sensory nuclei, that's what we're seeing here, because who cares? You're asleep. You don't need to attend to sensory information. It can still influence you. If there's a really loud noise, that'll make it through, but it has to be really loud. We've set the bar for excitation much higher because of the increasing firing of these particular neurons. On the other hand, all lanes of traffic are open for limbic input. So your memories can be consolidated when you sleep. Kind of nice. And this is just a bit of a summary over here of everything we see here. Those limbic reticular neurons, almost every single one of them has a decrease in firing when the animal's asleep compared to when it's awake. So since we're looking at the ratio of sleep to wake and the log of it, anything that's negative means that it's going to be more active in wake. So during sleep, there's a decrease in limbic inhibition. The limbic system affects the cortex. Are there any questions? Okay, let's take a moment and review these. Okay, so for the synaptic connectivity between our reticular neurons, what are we dealing with here? What kind of synapses?
Gap junctions.
Gap junctions, electric synapses. Exactly. So depending on what's going on in one neuron, it might be excitatory or inhibitory, it just depends. But it's direct charge transfer. What does that do for us? Exactly, it synchronizes their activity. So that those reticular neurons, they're involved with, let's say, a similar task like inhibiting vision, audition, they can all act together. So you get a little more synchronous activity. Now, they're not all coupled by gap junctions, but you'll get little units. Okay. How about with other neurons in thalamic nuclei? What kind of synapses are we forming there? What's that?
GABAergic.
GABAergic. Yeah, so chemical synapses and inhibitory. So inhibitory synapses here. All the other thalamic neurons that we were talking about, those core projection neurons, those are glutamatergic. That's all excitatory. The GABAergic input is, for the most part, going to come from your TRN. There's also, of course, local inhibitory interneurons as well. But these TRN neurons are a great source of kind of diffuse inhibition within a large area of the nucleus. How does that lead to selective attention then? That all makes sense? Who can walk me through this so we can leave here?
I can try to say some things.
Oh, thank you.
So when TRN activity is being increased, I guess like with their other nearby neurons, it's increasing input to the medial geniculate nucleus, and then the activity is inhibited. Whatever you don't want to do, that is in the lateral geniculate nucleus. Does that make sense? Any of that wrong?
I think it'll make sense. I don't know. Let's go through it a little bit at a time.
Okay.
Okay. What we're looking at here is activity in the reticular nucleus. Is that right?
Hmm?
Reticular nucleus?
Yep.
Okay, so same sets of neurons. In one case, we're paying attention to visual input, in the other, auditory input. Where are they targeting? Which part of the thalamus are they kind of diffusely inhibiting in this case? Do you remember this?
Somatic sensory.
The medial, you're talking about medial nucleus and lateral nucleus?
Yeah, which one of those are we dealing with here?
Vision is medial and or no, vision is lateral, auditory is medial.
Great. And so the reticular neurons that we're recording from in this case are going to project into the lateral geniculate nucleus. So these are your visual TRN neurons. The reason we call them visual is because they're targeted in the LGN. And it's GABAergic. Keeping that in mind. What do we see with the activity of these visual reticular neurons whenever we have to pay attention to visual input? When we want to pay attention to that,
Decrease.
there's a decrease in their firing. Great. So what happens to the excitability of your LGN? There you go. We're not inhibiting the LGN. What about when we want to pay attention to sound?
Then it would increase to inhibit it.
There you go.
It would decrease for your auditory. But
Yeah.
that-
Presumably, if we were to record from auditory TRN neurons, this would be flipped. When you want to pay attention to vision, inhibit the LGN. Doesn't matter. No. Jesus. When you want to pay attention to vision, inhibit the MGN. It doesn't matter. When you want to pay attention to auditory input, disinhibit it. This is for visual, so that's why we see this. In order to pay attention to auditory input, we're going to open up traffic in our LGN and inhibit the medial geniculate nucleus. Because neurons can only be so excitable, there can only be so much activity in the cortex. You can't turn the whole thing on, that's going to be a disaster. That's what we see in seizures. So that we have selective attention and selective excitation of the cortex, we determine what's the output in all these different nuclei here. Which ones are we inhibiting? Inhibit here, it's going to have less of an effect on your conscious perceptions. Any questions? All right. Well, I'll see some of you tomorrow and others 2 days from now.